We're excited to share with you about what covariance is, how it works, how it connects to things that we've already seen like variance and standard deviation, and also to things that we're about to see like correlation. Let's hop into the data and have a look together. This is a set of ordered pairs of performance data between U.S. stocks. It's weekly performance, by the way. U.S. stocks, international stocks, the S&P Volatility Index, which measures volatility in the U.S. stock market. And then we're also going to look at how did U.S. stocks do this week versus how did they do last week and see like, hey, is there a trading strategy in play where I could invest this week on the basis of how stocks performed last week? All right, well, cool. This is all data that I got off of finance.yahoo. What we're going to now look at are these ordered pairs, and we can see that when we're comparing the S&P 500, the U.S. stock market, to a large basket of international stocks, there is a relatively linear positive association. In other words, when the U.S. stock market does well, when it has good weeks, then international markets tend to also have good weeks. And conversely, when the U.S. has a bad week, the international markets also tend to have a bad week. There is a linear association here. Notice there's no explanation of causality. We're not saying that one of these causes the other to act or behave in a certain way. It's just that they're associated. We can look at how the U.S. stock market performs against measures of volatility in the stock market, the U.S. stock market. And when the U.S. markets are doing well, it appears that volatility tends to fall, it tends to go down. And conversely, when U.S. stocks are going lower or when they're having bad weeks, volatility in the stock market tends to go higher, right? So there is a somewhat linear association, right? There's a line we can imagine drawing. It is, in this case, a downward sloping line. It's an inverse relationship. And then finally, that trading strategy where we invest this week based on how stocks did last week just doesn't seem to be a good strategy. There's really no connection, right? I mean, sometimes you have good weeks followed by good weeks. Sometimes you have good weeks followed by bad weeks. Sometimes you have bad weeks followed by bad weeks. And sometimes you have bad weeks followed by good weeks. There's really no connection. There's no great linear association here. So this is real data, and it's a way of understanding what's going on under the hood when we're trying to work or get a sense from, what is covariance telling us or what is correlation telling us. I want to make another connection here and really emphasize that it is a linear relationship that covariance is reporting. Here, I have come up with observation X, observation Y. It is a perfect parabola, right? Y is just X squared. So when X is -4, Y is 16. When X is -3, Y is +9. There is definitely a relationship between X and Y. I don't know that it's a linear relationship like this title says, but the covariance turns out to be 0. There is no covariance because covariance is a linear measure of association. And while a parabola is definitely a relationship or a connection, it is not a linear connection. All right, we'll look at this formula again in just a moment, but before we do, it's going to make more sense if you understand what's really happening here. We're looking at ordered pairs, right? There's an ordered pair. There's an ordered pair. There's an ordered pair. This is in visual or graphic form, but we also have ordered pairs right here. Here's one data set, U.S. stocks, and here's another data set, international stocks, and I've got an ordered pair, an ordered pair, an ordered pair. You get the idea. But we have two variables, right? So in this particular week, when the U.S. stock market fell by 0.7%, the international stock market on that same week fell by 2.56%. Keep that in mind when I show you the formula in just a second. Great. Ordered pairs. Hope that you have them in mind. Well, first of all, variance is related to covariance in the same way that a square is related to a rectangle. With a square, we have all sides the same length, right? It is a rectangle, but where there's no variation in side length. And what we find is that the variance is an average. We're adding squared deviations that our actual data points live from the mean. So we have one variable, that variable is x. We take the mean of x, and then we look at the deviations. How far away does our data, each data point, live from the average? And we square that, right? And then we add them all together and we divide by the number of data points. Well, with covariance, instead of everything operating in one variable where we have one side length, we can operate in two variables where we have essentially, let's call this x's mean and then y's mean, and it's the same kind of formulation. We're adding up the products of deviations, and then we're dividing by the number of observations. And keep in mind, these are ordered pairs. So I'm looking at, say, observation 10, x took on a value and y took on a value. And I'm saying, well, hey, for observation 10, how did x vary from its mean? And I'm going to multiply that from how y deviated from its mean, and I'm going to do that observation by observation and add up all of the products of those deviations. And so that is really what covariance does, is it's just kind of a two-variable version of variance.